So now that we've dealt with projectiles launched horizontally, now we can launch them in angles. So if we throw an object up at some initial velocity and some angle, you know it's going to go up, but it's going to deviate from the straight line path because of gravity, and then it's going to come back down, and it's going to land some distance away. So we would break this velocity into two components. That's always going to be your first step. This is going to be the Vx component, and this is going to be the Voy component. Now, as this ball moves, when it's here, it's going to have the same horizontal velocity. Here, it's going to have the same horizontal velocity. Same horizontal velocity. Same right before it lands, so it hasn't touched the ground. Oops, that's a little bit long. Same horizontal velocity. Vertically, it's going to slow down, so it's not moving upward as fast. And then, at the very top, it stops in the up and down direction. It's still moving, but it's only moving horizontally. Then on the way down, I matched heights here, so it's going to recover the same amount of speed, but now the opposite direction. And then when it finally lands, we have the same vertical speed, but now the opposite direction. So if you land at the same height, the final velocity is equal to the initial velocity, but at the same angle below the horizontal. If I drew that, that would be here, and pretend those match. So this angle would be, if this is 60 degrees, this is negative 60 degrees, but it's the same amount of speed. Now, acceleration. I'm even going to write this, even though you know this. Acceleration is always 9.8 meters per second squared straight down. So if I ask you to type in an angle, you'd use negative 90 degrees. Straight down. Always, always, always. But how many times have I asked you in a different way? Like, what's the acceleration at the top? Oh, it's 0. No, it's not. It's 9.8 meters per second squared down. What's the acceleration here? What's the acceleration here? What's the acceleration there? 9.8 meters per second squared down. So, another fact I want you to remember is that if you launch something at an angle, like I'm going to say this is at really steep angle. So I'm going to say this is 5 meters per second at 70 degrees. And then if I launch it, same speed, but the complementary angle. Remember, complement means they add up to 90. So at 20 degrees, it's going to land at the same place. So this is 5 meters per second, 20 degrees. So complementary launch angles land at the same location if it's on a level field. If it's not a level field, then it's different. And since complementary means adds up to 90, this is why 45 degrees gives the furthest range, or the largest range. I don't like the way I said that. So 45 is its own complement. The difference between these two launches is at 70 degrees, it goes really high, but it's moving slowly sideways. Versus at 20 degrees, it's moving quickly sideways, but it doesn't go very high. And remember, height is what determines time in the air. So this spends a lot of time in the air, moving slowly sideways. Little time in the air, moving fast sideways. And they end up exactly complementing each other, complementary, and you land at the same place. The rest of this video is actually going to be working a couple of problems. So if you want to stop now with your notes, that's fine. If you want to watch the problems, that's fine too. So we're going to work this problem, and we have 3 different questions we're going to do for it, leading up to basically the landing location. So 70 degrees and 20 degrees. First, we want to know the maximum height. So height is determined by the vertical direction. So our first step is to figure out how fast it's moving upwards. VOY equals VO times the sine of the angle. So Here it's 5 times the sine of 70. Here it's 5 times the sine of 20. So I'm going to put those into my handy dandy calculator. 5 sine 70 is 4.6985, and 5 times the sine of 20 is 1.7101. And I'm keeping lots and lots of digits. Maximum height, the vertical velocity is 0. Only the vertical velocity. It's still moving horizontally. Let me move the notebook up. So if we're looking for height, that's displacement. We always know gravity. We know this is 0. We want to use the third equation. So Vy squared equals Voy squared plus 2Ay. Why? If I rearrange, this is y equals Vy squared minus Voy squared over 2Ay. So final is 0, minus the initial is 4.6985, don't forget to square, divided by 2 times, this is positive for upward, gravity's always down, so I need to make this negative. And so 4.6985 squared divided by 2 times 9.8, both negatives cancel out. That number does not make any sense. Try again. 4.6985 squared divided by, there we go, 1.1263 meters. And I'm still going to keep digits because we're going to use this for something in a second. Over here, we get 0 minus 1.7101 squared divided by 2 times negative 9.8, 1.7101 squared divided by 19.6. So we get a much lower maximum height as expected. Only 15 centimeters versus 1 meter and another 13 centimeters. So this is a pretty slow and low kick. Well, life goes on. Okay. Now, I want to know the total time. So there are a couple of ways to do this. The first one I'm going to show you is that if we look back at this picture, since we know it stops at the top, from the top, or excuse me, it stops vertically at the top, it's still moving horizontally, it's just like a horizontal launch. So if we look at only the second half of the motion, it's a horizontal launch. And you know, for a horizontal launch, Voy is 0, and we know the value of y. We know the distance it's going to travel down. So we can use the short version of this equation, t equals the square root, because this is 0, so 2y over ay. And because I'm talking about the second half of the motion, everything's down. It moves downward 1.263, and this is down negative 9.8, or down 9.8, so I'm just going to leave them both positive. Doesn't matter, make them both negative. The negatives will cancel. So the time for 70 degrees is the square root of 2 times 1.1263 divided by 9.8. Time over here is the square root of 2 times 0.1492 divided by 9.8. So second square root 2 times 1.1263 divided by 9.8 equals, this is 0.4794 seconds. That's not our answer because this is only the second half. So we need to double it to get 0.9589 seconds in the air. So repeat for this problem. Second square root 2 times 0.1492 divided by 9.8. 0.1745 seconds. Double it because we need the whole path. 0.3490 seconds. So higher, more time in the air. Higher, more time in the air. So now, where does it land? Oh, the times weren't on the screen. That's okay. It lands a horizontal distance away. You know that x equals vx times t. And the x component is the initial velocity times the cosine of the angle, and it's constant for the whole problem. So if I calculate Vx for this problem, 5 times the cosine of 70 degrees, I'm going to put that answer here because I'm running out of notebook. I get 1.710 meters per second, and my time is 0.9589 seconds times 0.9589, and I get a landing location of 1.64 meters. If I go over here, this Vx is 5 times the cosine of 20 degrees, so this x, if I put this here, 5 times cosine of 20 is 4.698, and our time is 0.3490 times 0.3490, 1.64 meters. They're the same. Here's the reason they're the same. It's all on the screen. Notice this y component is this x component, and this y component is this x component. And overall throughout this problem, because yes, there's a squared here, but there's a square root here, you end up multiplying the two components together. And the order of multiplication does not matter for scalar quantities. And so you end up with the same landing location. Okay, that's the end of that problem. There are two more things I want you to think about. So the other way to find the time in the air. Remember that when it goes up and comes down, whatever this velocity is matches this velocity, but below the horizontal, as opposed to above the horizontal. So if I go back to the previous problem, for 70 degrees, VOY was, let me just look on, 4.698 meters per second. So when this lands, it has the same vertical velocity because it's recovered the same speed. It's landing at the same height. Another way of justifying that is it slows down at 9.8 to the top, and then it speeds up over the same distance, so it's going to recover that same speed. But it's the opposite direction, so our final vertical velocity is negative 4.698 meters per second. And then we can use our favorite equation, the first one. Time is equal to Vy minus VOY over AY. So negative 4.698 minus positive 4.698 divided by AY. Well, it's down, and I'm using up in this problem as positive, so negative 9.8. So 4.698 negative minus 4.698, all divided by negative 9.8, gives me 0.959 seconds, which, if I flip back, that's what we got here before. It's a different way of doing it. You choose which way you want to do it. And the one I really want to suggest, and remember, this is the whole thing. We don't have to double this because we used the beginning of the problem and the end of the problem. The other way of doing it, we did the middle to the end. So we had to double it to get the whole thing. So if I give you a totally different problem, let's pretend I'm going to throw something off this building. So if this is a 50-meter tall building, and I'm going to launch this object at 20 meters per second at 53 degrees, you know it's going to go up and come back down. And if I would eventually ask you, hey, how far away does this thing land? You know how to find the x component. To find the time, you have some options. Vertically, the initial velocity is the initial velocity times the sine of the angle. So 20 times the sine of 53 degrees. 20 times the sine of 53 degrees is 16.383 meters per second. Now when this lands, it does not have that same vertical component downward, because that would occur right here at the same height. It's going to be going much faster downward than this because of this displacement. So you know the acceleration is negative 9.8 meters per second squared, and it's downward. So if I use positive for this one, I've got to make this negative. and it moves downward overall. Yes, it goes up something and then back down, but remember these equations are about displacement. So this is a downward displacement of 50 meters. Now, we need time so we can find this. You could use the second equation. Y equals VOYT plus 1/2 AYT squared. But this is not 0 anymore. So you can only do this with the quadratic formula. And I'll remind you, I love math, but I don't want to do the quadratic formula, except if I can use my calculator function with the solver. So instead, the way I usually solve these problems is referencing back, figuring out the final velocity, and then using the first equation. So you could use Vy squared equals V naught y squared plus 2AYY. Remember, when you take the square root, you get two answers. You would need the -1 because right before it lands, it's moving downward. Then you could use Vy equals VOY plus AYT to find the time, and then finally x equals Vx times t to figure out how far away it lands. Yes, it's a bunch of steps. Deal. It's gonna be fun.